let's say if I wanted to find the electrical field in this region, in the right region. So remember when we did this with in the electric field chapter, we said, oh, okay, if you're in this region, the electrical field of this is away from it. So if we call this, let's say, E2 second charge and the first charge, you said, oh, okay, the electrical field of this is this direction, E2. And then the electrical field of that, because it's a negative charge, is towards it, E1. So you kind of have to analyze the direction of the E field, right? And then you said, oh, okay, if I want to find the total E field in this region, I have to subtract their magnitudes in order to get the total E, right? But if I'm in this region, okay, the electric field of a positive charge is away from it. So then E2, right? So I'm calling this charge 2. And then the electric field of a negative charge is towards it, E1. Oh, okay, so then if I want to find the electrical field here, anywhere in this region, then I have to add their magnitudes. And then if I'm on this side, the electrical field of this guy, E1 is this way. And then the electrical field of that is away from it, E2. For a long time, the negative 2 is going to win. But remember, there's going to be a point way over there where the electrical field is 0. After that, the 5 nanocoulomb charge is going to win. So, so for now, near this charge, the negative 2 nanocoulomb charge wins. Okay, so then how would we approach this from a voltage point of view? If I'm on the right side, this equation becomes what? For absolute value, we can get rid of the absolute value sign because I'm greater than 2. So the absolute value of x minus 2 turns into x minus 2, and the absolute value of x plus 3 turns into x plus 3 if I'm all the way to the right region. So the general equation for the voltage becomes negative 18 over x plus 3 plus 45 over x minus 2. Now, if I want to find the voltage, what do I do? Negative dV dx, right? Then I just simply take the derivative of this. And then that gives me the voltage. I don't have to worry about, oh my gosh, the electric fields to the right, electric fields to the left. When I do this, it will already take care of that. That's the cool thing. I take the derivative of the voltage. So then what's the derivative of this? 1 over x plus 3, the derivative is negative 1 over x plus 3 squared, right? So it'd be 18 over x plus 3 squared. And then the derivative of this will be negative 45 over x minus 2 squared. And then, of course, the derivative of the inside, which is 1, and the derivative of this is also 1. Negative is still here. I never utilized this negative. I'm like, what happened? What did I do wrong? I'm like, okay. I never actually utilized this negative. In other words, when I took the derivative of this, that already gave me, when you take the derivative of 1 over x, you already get negative 1 over x squared. So that canceled that, and that's this. And the derivative of this is this. But I never utilized this negative. E is negative. So now if I utilize this negative, what am I going to get? This goes there. Oh, wonderful. This distributes there. There you have it. So without even us worrying about, oh, the electrical field of a positive is away from it and the negative is into it, and then this wins this, so the total electric field is to the right, this already has that taken care of. As long as you've got the voltage sign taken care of, then if you take the negative derivative of it, it's going to give you the correct general equation for the electrical field. It's amazing how that works. So now, how about in the middle? What does the voltage equation turn into in the middle here? So negative 18 over absolute value of x plus 3 plus 45 over absolute value of x minus 2. So if you get this equation correct, then you just have to do the negative derivative of that, and that will take care of itself. So then what happens when you're in this region? You are less than 2, so this absolute value turns into negative of itself. So I'm using this property of absolute values. Absolute value of x is x if x is greater than 0, negative x if x is less than 0, right? So in other words, when I'm less than 2, this is going to be a negative number, so I need to put another negative to get rid of the absolute value. And then this, I'm still to the right of that, so it's still x plus 3. So the general equation for the voltage in the middle region is going to be negative 18 over x plus 3. But then this one is going to be negative of itself. So negative 45 over absolute value of x minus 2. Okay? Now, take negative the derivative of that. And that will already take care of the fact that the electrical field is in the same direction. You see? So E negative dV dx. Well, what I could do in this case is distribute the negative in first. So negative into this and into that. So it'll be dV. It'll just be, this negative will make both of them positive. Right? And then take the derivative of that. So negative 18 over x plus 3 squared, negative 45 over x minus 2 squared. There you have it. So it's already telling you that the electrical field is both of them to the left. You see? Both of them are to the left. So to find the electrical field, you just add them, and then you put a negative there. Isn't that crazy? As long as you got this correct, negative the derivative of that takes care of the direction of the electrical field. Okay, so then how about in the left region? Left region, what's the correct equation for the voltage? Then this would be, the absolute value would be also negative of itself, and this would be also negative of itself. So then this one, you would say 18 over x plus 3. And then this one would be negative of itself, 45 over x minus 2. Okay, then take the negative derivative of that again. Negative dV dx. And then you're going to have here, the derivative of this is already going to be negative. So negative of negative 18 over x plus 3 squared. And then the derivative of this is going to be negative of itself. So plus 45 over x minus 2 squared I hat. And then distribute the negative in. So 18 over x plus 3 squared minus 45 over x minus 2 squared. So it's saying take the 18, right? So take the 18 and then subtract from it the 45. Is that what happens? Yep, the E1 wins, and then subtract from it the electrical field of that guy. So it's just crazy that how that works. So now how about if I want to find the electrical field anywhere in space, right? Such as the point 1, 4. Right? So how would we have done this? For voltage is a lot easier, as you guys saw. So how would we have done this for electrical field? Well, we say the electrical field of this is towards it. The electrical field of this guy is away from it. So it is pretty tedious, you know. Then you have to break this into components, break that into components and add them. So the voltage way to approach that would be to say, find the general equation of the voltage at any point, xy. So then it's going to be negative 18 over square root of x plus 3 squared plus y squared plus 45 over square root of x minus 2 squared plus y squared. Okay, so now the electrical field is going to be negative partial derivative of v with respect to x I hat, negative partial v partial y j hat. The electrical field is going to have two components at any random point. So if you hold the y constant, take the derivative of this with respect to x, that gives you the electrical field in the negative direction. In the x direction. Then you do minus, hold the x constant, take the derivative of it with respect to y. So it becomes more like a calculus approach of finding the electrical field. You see? So then what would that be? The derivative of this with respect to x would be 1/2, negative 1/2. Okay, so the negative half goes to the numerator, becomes negative half. Then it comes out in the front, so then it becomes 18 times half, and then times the derivative of, so then it becomes x plus 3 squared plus y squared to the 3/2 power, right? So whenever you have something like 1 over square root of x, the derivative of that is what? It's x to the minus half. So the derivative of that is going to be negative half x to the negative 3/2. And of course, if that's something where you have to take the derivative of that again, then you say, okay, then use the chain rule. So it's negative 1 over 2 x to the 3/2 times the derivative of the inside. So that's what I'm doing here. The derivative of this guy is going to be negative of itself. I'm not applying this outside negative yet. So then the negative 18 times 1/2 times this thing to the 3/2 power times the derivative of the inside with respect to x. So what's that going to be? 2 times x plus 3. All right. And then same thing here. Plus 45, negative half times the derivative of the inside, 2 times x minus 2 over the whole thing to the 3/2. So I just did this portion of it. That gives me the general equation for the electrical field in the x direction at any point in space. You see? Let's continue it. Okay, let's see. So if I simplify that, I get electric field. The 2's cancel. So negative 18 x plus 3 over x plus 3 squared plus y squared to the 3/2 minus 45 times x minus 2 over x minus 2 squared plus y squared to the 3 halves. And then I hat. You see, so notice where the 3 halves is coming from. So when we calculate the electrical field, we usually get 3 halves, right? Because we do the distance, then we take the sine or cosine of the angle. So in the x direction, this is actually the cosine of the angle, right? X plus 3 over, and then you get this to the 1/2 power. And then x minus 2 over this to the 1/2 power. So you're getting that already by just differentiating it. Okay, and then in the y direction, you're going to get what? Minus, then you're going to get 18 times 2y when you integrate it. So, so 18y over x plus 3 squared plus y squared to the 3 halves minus 45y over x plus 3 squared plus y squared to the 3 halves, j hat. So it looks very similar to the x equation. It's the derivative of the voltage with respect to y while holding x constant, right? Now, the last step would be to distribute that negative, the negative dv dx, negative dv dy, right? So distribute this negative, and then this one will make this negative and make that positive, and then distribute this negative. So I'll just write positive here, distribute this negative, and go like this. So then if I wanted to find the electrical field that's at 1,4, just like I found the voltage at 1,4, now this is when I would put the, after taking the derivative, then I would put the components for the x, 1,4. So I would put 1 here, and then 4 for that. So negative 18, 1 plus 3, and then here I would put 1 plus 3, 4 squared plus 4 squared to the 3 halves, plus 45. And I would put 1 here. Then you get here 1 minus 2, 1 squared plus 4 squared to the 3 halves. Then plus, then I would put 4 here, negative 72 over, and then this part is going to be the same. 4 squared plus 4 squared to the 3 halves. And then plus, and I would put 4 there, 45 times 4. And then I would get the same thing as there. 1 squared plus 4 squared to the 3 halves, j hat. So that would be the general way of finding the electrical field at any point in space. So with 2 charges, you might say to yourself, well, why do we even need this technique if I can find easily the electric field of 2 charges?